Hello everyone, let's start our next lecture on thermodynamics. After zeroth law of thermodynamics, our today's topic, there are a lot of topics today. There's a mechanical work, internal pressure, external pressure, isothermal, irreversible and reversible work by ideal gas, and proof of W reversible greater than irreversible work. But before starting our journey today, I have to start from the last slide that I showed you in my last lecture, last class, where there were the definition of work, different definitions of work. There had been 5 definitions of work, out of which kinetic work is force into displacement. This is, you are most acquainted with this definition, okay? And what you have to do right now is mechanical work. Mechanical work is the pressure into volume change. Pressure is the intensity factor, volume change is the capacity factor. Okay, so with this relationship we would move to our next discussions. So let's start with mechanical work. So mechanical work is actually movement of an object due to pressure difference. Kinetic work, what was kinetic work? Kinetic work was actually the movement of object due to difference in force, unbalanced force. Okay, that is kinetic work. But if it is due to unbalanced pressure, then it is mechanical work. And that pressure is the intensity factor, and the product of intensity factor and capacity factor, the capacity factor is the volume change due to difference in pressure, and this is actually work done. Suppose this, in this example, here is a piston which is containing some gas, maybe some ideal gas, and preferably some ideal gas, and this piston is actually there are 2 actually weights are given on it, okay, which is balancing the internal pressure with the external pressure. So this is actually a symbol of external pressure. If one is moved from here, okay, one is removed from here, then the external pressure decreases, and if another one is placed above it, then the external pressure increases. Now if we remove one weight from here, or if we put another weight on here, then there would develop the unbalanced pressure. If the pressure is decreased, then the piston would move in the upward direction. That means the system is now working. The internal gas is pushing this piston in the upward direction against the pressure which is coming from the upward from the external side, which is known as the P external pressure. So against P external, the piston is actually working, and since the system is working, that is why the negative sign is given, as I have said in my last class. So here in this case, if P external is less than P internal, then the piston would move upwards, that is, work would be done by the system, and the mathematical expression of work would be minus P external into delta V. Delta V is this portion change in volume, the volume change in this portion. And similarly, if the pressure is increased by putting extra weight on the piston, then the P external would become greater than P internal. In that case, the surrounding is working. That means the work is being done on the system, and here the work is being done against pressure P internal. Okay, what is the internal pressure? Against that pressure the piston is moving, isn't it? So in that case, the work expression should have a positive sign, and the product of P internal and delta V, that is the volume, the decrease in volume, is actually the work done. So these are the expressions of mechanical work, and if P external and P internal are same, then no work would be done. And in another case, no work would be done if some piston is moving against vacuum, because if the piston is moving against vacuum, then it is actually pushing nothing. It is actually moving against zero pressure. So the intensity factor becomes 0, and in that case the work done becomes 0. So what you have to keep in, you have to note here, so it is to be noted that work done on expansion against vacuum is nil. Okay, so no work is done. Now our next topic, isothermal reversible work of ideal gas. Okay, so suppose here is some ideal gas, and there are 2 weights here. One is removed, so the external pressure decreases, and that external pressure from P prime PEXT prime to PEXT. Okay, the internal pressure had been first P1. Now since the pressure has been released to some extent, it has decreased and it has got the value P2, and volume also increases from V1 to V2, but throughout this operation the temperature of the system remains constant, and that temperature is T. Okay, now at this, since this temperature is constant, so this is an isothermal expansion. Now this is irreversible expansion. Why this is irreversible expansion? Because this weight has been taken out at once. Okay, not in parts. Suppose you have just taken it out, so suddenly the piston would move towards the upward side. So this type of work done would be actually irreversible work done, because this process is fast and it takes place in one step, not in several steps. Okay, now when this external pressure becomes equal to the internal pressure, that means P1, then it would this P1, actually P external dash would be equal to P1. Then in that case it will get equilibrium, and until then some work would be done. So the external pressure irreversibly decreases from P dash, actually P external dash to P external, which is equal to the final pressure P2. So since the final pressure is P2 and since these two have become equal, so this P external is actually the final pressure P2. Is that point clear? That means the initial pressure had been P1, now the pressure has decreased to P2. That means the piston was moving upward against the pressure P2, which is actually the P external pressure P external. So in place of P external we can write here P2. So always we have to write P2 in case of external pressure if it is irreversible expansion. Okay, and in case of volume we have to take the volume change, that is V2 minus V1. How? Look, therefore the gas expands against pressure P external, which is actually P2. Okay, therefore the work done by the gas, so since the gas is doing the work, that is the system is doing the work, so it will be given the negative sign. So here the negative sign, so minus W. Now what about these suffixes? Actually IRR means irreversible. Okay, ISO means isothermal, that means it is taking place at constant temperature, and ID means for an ideal gas. So this is actually, we have to do the integration of intensity factor and capacity factors product. Okay, what is the product of intensity factor and capacity factor? It is P2 dV. P external dV, but actually this is nothing but P2 dV, because P2 is the final pressure, which is actually equal to the P external pressure. Okay, and what was the limit? The limit was the actually the initial volume was V1 and the final volume was V2. So the limit is actually, lower limit is V1 and the upper limit is V2. So integration V1 to V2, P external dV is the expression of minus W irreversible isothermal for ideal gas. Okay, now since this P2 is some constant pressure, because suddenly you are taking out the weight, so whenever you are taking out the weight, then it is becoming equal to P2. So this is a constant pressure, so that is why this constant term is taken out of the integration sign. So this P external is, before integration sign you can write the P external, and here you have written it here P2. Okay, and the other things are same. Integration V1 to V2 dV is also same here. Now simple integration V1 to V2 dV is nothing but V2 minus V1. So since it is an ideal gas, so instead of V2 you can write nRT by P2. N is the overall number of moles of the gases and P2 is the final pressure, whereas in place of V1 you can write nRT by P1. Since the temperature is constant, so there is no T1 or T2, just it is T. T is the temperature in which condition it is taking place. Now taking nRT as constant and putting P2 inside the bracket, you can get the relationship what? P2 by P2, that means 1, and here P2 by P1, so as it is P2 by P1. So this is the final expression of isothermal irreversible work done by an ideal gas. So we have one expression here, minus W irreversible isothermal ideal gas equals to nRT 1 minus P2 by P1. This is one expression. Now let's move on to our next heading, which is isothermal reversible work by ideal gas. Okay, till now we have done isothermal irreversible work. Now if the weight is taken in parts, suppose that is a 1 kg mass. Okay, so if you are taking out the weight by 1 gram, okay, first time it was 2 kilogram overall, 1 plus 1 2 kilogram, and it is now 1 kilogram 999 gram. Then second time it is 1 kilogram 998 gram. The third time 1 kilogram 997 gram, and this way you have removing the weight by 1000 times. Then you are becoming 2 kilogram to 1 kilogram. Okay, and the pressure is also not constant, it is variable, it is changing from P1 to P2. So in this case you cannot take this pressure term out of the integration sign, because this time this pressure is not constant, this pressure is a variable. Okay, so let's proceed at temperature T, which is a constant temperature, and the initial pressure is as usual P1 and initial volume is V1. Now external pressure, which is reversible step by step, decreases from P1 to P2 so that the gas expands to its final volume V2. Okay, so the gas is expanding from V1 to V2, its final volume. In this context, actually there had been a number of steps, 1000 number of steps, or the number of steps as much as high you can think it, because this is a reversible process and it is taking place always in small steps. Therefore the expansion of the gas does not take place against any constant pressure, so the pressure term becomes variable here. So if the pressure decreases by dP, every time the pressure is decreasing by dP, so what should be the final pressure? The final pressure should be P minus dP every time. Okay, then it can be said that the gas expands against pressure P minus dP, isn't it? Now what should be the expression of work? The work here suffixed REV means reversible, ISO means isothermal, ID means ideal. So for an ideal gas, the work done in isothermal and reversible condition should be integration, its lower limit should be V1, upper limit should be V2, and the external pressure, instead of external pressure you can write here P minus dP, because the gas has expanded just dP short of P into the volume change, which is dV. So we can just divide this into two parts, this one is as PdV and this one as minus dPdV. Okay, and doing the integration, same integration, but this term is to be neglected because multiplication of two derivatives, two differential terms is very negligible, so this is neglected. So only the term remaining should be integration V1 to V2 PdV. Okay, so here you have to mention this also, because since dPdV is too small and hence integration V1 to V2 dPdV is neglected, you have to mention this. Now this one, in place of P you have to write nRT by V, since this is an ideal gas, because you have to get the variable term in terms of V, because the limits of the integration sign are volumes. Okay, so V1 to V2 nRT by V. So you can easily integrate this. Actually dV by V integration has the result ln V, and if it has upper limit V2 and lower limit V1, then it is definitely ln V2 by V1. So nRT is the constant term and the result of the integration is nRT ln V2 by V1. So this is the final expression. So what is the difference with that one, with the previous one? The difference with the previous one, that the pressure term is not kept outside the integration sign, it is always kept inside the integration sign, first of all, and secondly the pressure is not at all constant, and that is actually instead of external pressure P2 we have written here external pressure P minus dP. Okay, so this is the difference, and the expression of work done by the system is nRT ln P1 by P2. So you have to keep them in your mind. So two things are done. Now finally we have to prove that the reversible work done is actually greater than irreversible work done. Now you may have one question in your mind. In this expression we are giving the modulus sign. Why this modulus sign? Because suppose this system is working minus 3 joule of work and this system is working minus 2 joule of work. So which one is greater? mathematically minus 2 is greater than minus 3, but you can understand easily that minus 3 joule of work means it is doing more work, and minus 2 joule of work means it is doing less work, but mathematically it's not being supported. That is why we are putting the modulus sign here in order to just cancel the sign terms. Okay, so that is why modulus term. Now we have to memorize the mathematical expressions of work done by the system for both reversible and irreversible case. And as we have got two equations for reversible work done, it should be RT ln P1 by P2, and for irreversible it is RT into 1 minus P2 by P1. Okay, we have just omitted the term N, which is the number of moles of gases, because we have taken here 1 mole of an ideal gas. Okay, so let's start. As we have the expressions of W reversible and W irreversible for isothermal expansion of ideal gas, the difference of their magnitude irrespective of their sign is this one. So magnitude work done by the system reversibly minus the work done by the system irreversibly within the modulus. So their expressions are RT ln P1 by P2, and here irreversible expression is RT into 1 minus P2 by P1. And here you have to mention that you have taken 1 mole of an ideal gas, that is N equals to 1. Okay. Now for small changes, if P1 there is not so much difference between P1 and P2, then you can approximately write ln P1 by P2 P1 minus P2 by P2. Instead of ln P1 by P2, what you can write? You can write P1 minus P2 by P2 if there is small difference between P1 and P2. That is, the change in pressure is very small. Okay, so you can write this expression. What we have written here? Instead of ln P1 by P2, we are writing here P1 minus P2 by P2. And here the expression is same, just taking the LCM of the denominator. Okay, here the denominator is 1, here the denominator is P1, so LCM is P1. So LCM is divided by the numerator and multiplied by the divided by the denominator and multiplied by the numerator. Okay, so this way this is P1 minus P2. So this P1 minus P2 seems to be constant here, so you can take this P1 minus P2 as constant, along with RT also constant. So what will be left after taking the constants? Here 1 by P2 and here minus 1 by P1. So in the next slide we are writing this same thing, RT common, P1 minus P2 common, just uncommon things is 1 by P2 minus 1 by P1. Okay, now take the LCM of P1 and P2, and then in the numerator you can get P1 minus P2. This P1 minus P2 is multiplied by P1 minus P2 again, that means it becomes the square of P1 minus P2, and in the denominator is actually the LCM of P2 and P1, that is P1 into P2. Okay, and this term is always should be positive. This term should always be positive. Okay, this is a positive term. Why? Because there is a square term. So the difference in pressure, whatever be the difference in pressure, if the difference is positive or if the difference is negative, in both cases its square would result in some positive term. And regarding this one, R is positive constant, temperature can never be negative in the absolute scale, and P1 pressure is always positive, P2 pressure is again always positive. The difference may be negative, but still, since there is a square term, so the overall term is always positive. So difference A minus B, if A minus B is positive, that is A greater than B. So W reversible minus W irreversible, if it is positive, that means W reversible is greater than W irreversible. So we can conclude that the reversible work done by the system is always greater than the irreversible work done by the system. So if you are doing the work in one step, then actually you are doing some less work. Or on the other hand, if you are doing the work in several steps or in small steps, then you can conclude that you are doing some more work. Okay, so we have come to the conclusion that W reversible is greater than W irreversible. So that's all about our topics today. Thank you. Have a nice day.